Well, we'll analyze the normal curvature. So consider the surface patch sigma and consider the first fundamental form of it. What is the first fundamental form of the surface patch sigma? It's E du square plus 2f du dv plus g dv square, okay, with the usual notations E, F and G. What is the matrix representation of this? Du dv E, F, F, G, du dv. Let me consider this matrix E, F, F, G. Let me denote it by cap F1. Okay, so F1 is E, F, F, G. This is the matrix. Similarly, consider the second fundamental form of sigma. What is it? L du square plus 2m du dv plus n dv square. And what is the matrix representation of this? Du dv L m m n du dv, right, the product. So now let me represent this matrix as F2. So F2 is equal to the matrix L m m n. Now let me consider two vectors T1. Okay, let it be equal to xi1 sigma u plus eta 1 sigma v. T2 is equal to xi2 sigma u plus eta 2 sigma v. Linear combination of these tangent vectors. So T1 and T2 are tangent vectors at some point of sigma, right? So these are tangent vectors at some point of sigma. Now let us consider the dot product T1 dot T2. Okay, so it is equal to xi1 sigma u plus eta 1 sigma v, the dot product with xi2 sigma u plus eta 2 sigma v, right? So consider the dot products and we are going to get it after some steps of calculation. We will arrive it at E xi1 xi2 plus f into xi1 eta 2 plus xi2 eta 1 plus g into eta 1 eta 2, whose matrix representation is xi1 eta 1 into the matrix E, F, F, G into the matrix xi2 eta 2. Okay, now let me represent the matrix, the transpose of this I will take. So let me take it as T1. So let T1 be equal to the matrix xi1 eta 1 and let me take T2 for the matrix xi2 eta 2. Okay, let us consider these two. Then what will be the dot product here? T1 dot T2 vectors dot product. This is, it is the transpose of this. So T1 transpose into, what is this matrix? It is F1, right? So F1 and this matrix is T2. Okay, so the dot product of the tangent vectors at some point of sigma is given by T1 transpose F1 T2. Let us call this as the statement 1. Now let me consider the unit speed curve gamma of t, right, which is given by sigma of u of t, v of t, a unit speed curve. Then what is gamma dot of t? Gamma dot of t is given by the derivative of sigma with respect to u and u with respect to t, and the derivative of sigma with respect to v and v with respect to t. Now if I consider t, the vector t is equal to the matrix u dot v dot, right? Then by the previous proposition, an expression for the normal curvature, what we have? Kn is equal to L u dot square plus 2m u dot v dot plus n v dot square, okay, whose matrix representation is u dot v dot L m m n u dot v dot, right? So this Kn will be equal to, the normal curvature will be equal to u dot v dot. What is it? It is the transpose of this matrix. So T transpose, and this matrix we have taken it as capital F2 and this is T. Okay, so the normal curvature expression we have here. So now with the help of this F1 and F2, we will define the principal curvatures of a surface patch. So what are the principal curvatures of a surface patch? The principal curvatures of the surface patch are the roots of the equation determinant of F2 minus Kf1 is equal to 0. Okay. So what is this determinant of F2 minus Kf1? I can represent it as F2 minus Kf1. F1 is the matrix EFFG. F2 is the matrix LMMN. Right. So what is it? It's the determinant of L minus K into E, M minus K into F, M minus K into F, right? N minus K into G. So this is equal to 0. So whatever equation we have, we will find out its roots. Those roots are called as the principal curvatures of sigma. Okay, now when you expand it, and you will see that it's a quadratic equation for K. So how many roots will be there? There will be 2 roots. It's a quadratic equation, so there will be 2 roots. They are in fact real roots. We are going to prove in the next class here that they are the real roots. Okay. Now if F1 is the identity matrix, so for example, if you consider the parameterization of a plane, then F1 is going to be the identity matrix. Then this statement, if I call this as the statement 3, both are same. So statement 3, then this becomes the equation for the eigenvalues of F2, because F1 is the identity matrix. So it is nothing but the eigenvalues of, because it will be F2 minus K into the identity matrix, right? So it will be the eigenvalues equation for the eigenvalues of F2. But what is F2? F2 is a real symmetric matrix, right? LMMN. It's a real symmetric matrix. Hence, the eigenvalues of a real symmetric matrix are going to be real numbers in that case. Okay. So if that is if F1 is identity matrix. If F1 is not identity matrix, even if it is not identity matrix, it is always invertible matrix, right? Why? Because what is F1? F1 is EFFG, right? And what is its determinant? Its determinant is EG minus F square. And what is EG minus F square? If you remember the earlier formula, it is sigma U cross sigma V norm square. And for a regular surface patch, what is this? It is never equal to 0. Okay, so even if F1 is not the identity matrix, but it is always invertible. Okay, so I can write the equivalent statement for this in another form. So what is that? It is nothing but determinant of the matrix F1 into F1 inverse F2 minus K into the identity matrix. This is equal to 0. It's the equivalent statement for this here. So what do I get here? It is nothing but determinant of F1, right, into determinant of the remaining part, that is F1 inverse F2 minus K into the identity matrix, that is equal to 0. But we know that this is not equal to 0, right? It is invertible matrix, so the determinant is not equal to 0. So from this what we get? This must be equal to 0. Okay, so the principal curvatures are the eigenvalues of the matrix F1 inverse F2. Okay, but this is not usually a symmetric matrix. It is not usually a symmetric matrix. Okay, so now if K is one of the principal curvatures of sigma, then F2 minus KF1, okay, it is not invertible. Okay, by the statement 3. By statement 3, Kf2 minus Kf1 is not invertible, right? So assuming that this is real, okay, if I assume that this is real, then I can find a non-zero 2 by 1 matrix, okay, 2 by 1 matrix, that's a column matrix, let me call it as T, whose entries are real numbers, such that F2 minus K into F1 into this matrix T is equal to 0. Okay. Now if the matrix, if I consider the matrix T is equal to xi eta for this vector, if I consider it as the column matrix having entries xi eta, if it satisfies the equation, this one, if I call it as statement 4, then the corresponding tangent vector, what is the corresponding tangent vector? It is the xi sigma u plus eta sigma v. If I call it as t, okay. So the corresponding tangent vector to the surface sigma is called as the principal vector corresponding to the principal curvature K.